Welcome to Soil Mechanics. I'm Dr. Don Warrington, and this is the introductory slide presentation to this. In doing this, I want to make something somewhat clear, and that is this. Usually, introduction, my students look at it, and he just goes through a lot of, kind of fluff and that kind of thing, and then they, kind of ignore it, and a lot of times they don't even watch it. This introduction is a little different in that not only we're going to do a general introduction to geotechnical engineering and soil mechanics, but we're also going to get into some little bit of engineering geology. And I say a little bit because, unfortunately, we don't have time for any more than just a little bit of engineering geology. So with that, let's get started. We're going to have a definition and overview of geotechnical engineering, and then some basic engineering geology. Civil engineering is a surprisingly broad field, and the fields don't always complement each other from an intellectual or a pedagogical standpoint the way that you'd like them to, which is one of the reasons why, even though the rest of the engineering majors kind of make fun of civils as the easiest, in some ways it's a little different. It's different in that the different kinds don't always have the same logic to them. You have structural engineering, engineering mechanics, transportation engineering, environmental engineering, which is becoming increasingly important, and then you have coastal engineering. And then the last we're going to talk about, and this course and foundations, which comes after it, deals with, is the issue of geotechnical engineering. So we ought to say, what is geotechnical engineering? Geotechnical engineering is the branch of civil engineering that deals with the properties of soils and rocks and their capability of supporting structures placed on, next to, or under them. And that's about as simple as it gets. Most of the deal with civil engineering talk about stuff above ground, and its structural capabilities or its ability to handle, in transportation we talk about moving cars or other types of modes of transportation over it or through it. In geotechnical engineering, we are talking about the foundation, and actually, geotechnical engineering is foundational in more ways than just the topic, because no building on the earth, and the ones in the space were launched from ones on the earth, no structure is any better than the foundation that's under it. And that's one reason why geotechnical engineering is of a lot greater interest to practitioners in general than it is to many students who are looking for career options or whatever. So it's important. It's an important field, and one that doesn't always get the due. Depends on the institution, of course. At this institution at UTC, traditionally geotech has not been a major component. It's gotten greater because of the interest of employers as much as anything. The geotechnical engineer works in a complex environment. To say that soils and rocks, particularly soils, are not conventional engineering materials. They tend to be, they're variable in quality. Their formation is complicated. It's taken a long time to get them there. They were not done under controlled conditions, and they vary widely even at one job site. They require a higher degree of judgment than other branches of engineering. And it's one thing I try to instill in my students is a taste of that type of engineering judgment. There is more than one acceptable solution to any problem. Some acceptability comes in many forms. There is, of course, economic acceptability. There is structural and integrity, both against catastrophic failure and against excessive settlement. We'll talk about these terms over and over and over again in this course, and especially in foundations. But there's also environmental considerations, And in fact, environmental engineering and geotech are very closely related to each other in many ways. And many of the skills you have in one, you also apply in the other one. And frequently, in order to solve environmental problems, you have to construct geotechnical structures. And the integrity of the structure above is dependent upon the quality of the foundation below. And I can't overemphasize that. Development. We've been putting buildings on foundations since the beginning of civilization. And it's, however, it's been the two things. First of all, it was empirical. All of our, until, I don't know, maybe the 18th century, most of what we did in civil engineering was empirical. Geotech was the slowest to see that change. It was the slowest branch of civil engineering to develop a theoretical basis that could be used in practical design. And the design of foundations was traditionally conservative and the result of trial and error. When we started to make the thing that really kind of pushed geotechnical engineering into doing something about its empirical roots was in the 19th century. We started building larger structures, skyscrapers, large bridges and whatnot, and railroads as well. These were heavier, larger, taller, whatever, and they led to some very catastrophic failures. And they were forced engineers to develop some kind of theory to predict. And that theory didn't necessarily have to be particularly sophisticated, although it was in some ways. But we cannot, and I kind of beat this drum all the time, we cannot base our engineering on purely empirical design. We have to have some type of underlying theory one way or the other. And that was true in geotech as well. And even with the relatively primitive state of the theory, we were able to move the design of structures forward significantly. For example, 1916, Gothenburg in Sweden experienced a harbor failure. They had built a nice quay along where the ships could pull up to, and one day that quay basically slid into the harbor. And what they discovered, as you see in that diagram on the left, is this: they had built it and they had put nice piles in it and whatnot to keep it from sinking. But what they didn't really think about was the fact that underneath there were soft clays. And soft clays are usually the beginning of trouble on a lot of job sites. And basically what happened was that a circular or semicircular or segment of a circle basically failed, and a large mass of soil rotated around those O-shaped things at the top, and they basically failed. And the elevation not only dropped, but the quay actually moved out into the harbor. And suddenly somebody realized that somebody else, or maybe even themselves, had not taken into consideration important things in the design of this. They were also having the same problems with railways, and if you look in the beginning of your book from Roy, you'll see another one of those. In 1913, the Swedish State Railroad Administration appointed a special geotechnical commission to study these types of failures and recommend a solution. And its chairman, Walmar Fellenius, developed the basic analysis methods for analyzing rotational failure of slopes, which is basically what happened in the Gothenburg Harbor as well. And we're going to talk about that towards the end of the course, which with improvement we use today. Same methods. And the name Fellenius is going to turn up again. The Felleniuses are a very illustrious family of Swedish and Canadian geotechnical engineers, and you're going to see that name again. The individual, however, that probably had more to do to really move make the theory informative, let's just put it that way, was Carl Terzaghi. He is called the father of geotechnical engineering, I think with justification. He developed both the theory and the practice of the analysis of soils and design foundation. Now, there had been theory before him, particularly with retaining walls, permeability and whatnot, had all developed, and some of the use of theory of elasticity had all been developed before Terzaghi. But Terzaghi advanced it in a number of important places. One, consolidation theory. The second is the bearing capacity of shallow foundations, which we'll talk about consolidation in this course. We'll talk about the bearing capacity in the foundations. And the design retaining walls for retaining walls and circular cofferdams is also a major advance of Terzaghi. He also wrote some of the first textbooks, and I say the first textbooks. There were textbooks before Terzaghi, but really, if I were to make his original Soil Mechanics and Engineering Practice as a textbook, I could use most of it today, after all these years. And he also did theoretical soil mechanics, which was a major entry into that field as well. So with that, we've gone over a very brief interview, and we're going to talk about soils and rocks. And this is important not only because as we see both in the geotechnical environment, and we need to understand the relationship between the two, what's different between one and the other, and that sort of thing. When we consider soils and rocks, we need to determine which is which. Definition of rock and soil. First of all, a rock is a naturally occurring material composed of mineral particles so firmly bonded together that relatively great effort is required to separate the particles. Either you have to blast them or crush them or somehow wedge them apart. They are generally cemented. They have lower porosity than soils, although they're not entirely unporous. Those of you who buy granite countertops for your house will find that they're sealed because they are natural rocks and they are porous. Their properties are much more variable due to weathering, and we're going to talk about weathering in a minute. They're often discontinuous and they have very complex stress histories. Most all materials in the earth started out as rock. Soil, on the other hand, is naturally occurring mineral particles which are easily separated into relatively small pieces, where they're granular in nature. Sometimes the grains are large, like they are with the gravel. Sometimes they're small, like they are with the clay. But they're granular, generally. They're rarely cemented. You do see them some with clays, higher porosity, less variable due to weathering and decay. They're usually continuous. You don't have the large cracks and fissures, generally speaking, unless you're talking about certain types of clays, as you do with rocks. And they have more predictable stress histories. Rocks, just as an aside, generally tend to have greater strength than their soil counterparts. It's just that the cracks, you have to watch for them. And of course, those particularly in this part of the country, we see rock slides. I think we understand that sometimes rocks don't perform the way we would like them to. We're going to go over briefly some of the minerals that form rocks, the feldspars, most igneous rocks, which basically come out of a volcano of some kind. And they tend to weather the clay minerals. We're going to talk about clay minerals in just a minute. They can, and that of course, and that of course, the fact that they're feldspars come from feldspars, and then there's a lot of chemical weathering as well, in addition to just weather. I'll talk about that. You also have quartz. Quartz is basically what glass is made of. It's a very hard, transparent, translucent material. It has a shell-like fracture. The soils which are purely, you see, of course, quartz in the environment as quartz crystals and whatnot. But the most common thing in soil mechanics, the most common use, the most common appearance of quartz is in sandy soils. Generally speaking, most sandy soils are what we would call silicaceous. Since it's silicon dioxide, quartz, any soils which are based with quartz particles are silicaceous. They are virtually unaffected by chemical weather, and they're very difficult to break down with chemical processes. And then there's calcite. On the other hand, it very colorless to white mineral. If it comes into contact with with hydrochloric acid, it will generally dissolve in one way or the other. There are two very important types of soils we see calcite in, and it degenerates to. One of them are calcareous soils, which are seashells, coral skeletons. These are living creatures that have died. They have basically, I guess, petrified is one way of putting it, and then they perhaps decompose into calcareous soils because they are carbon based as opposed to silicaceous, which are silicon based. If you look at your periodic table, you'll see why this is easily so. Calcites, even in the rock form, will weather and dissolve. In this part of the United States, we have what we call karst topography. And karst topography is created basically by calcites, by calcareous soils, or calcareous rocks, actually, breaking down through weathering processes, which don't necessarily need to be out in the open. They can be inside. They can be in caves and whatnot where water runs over them, and water mixed with acidic dissolves the rocks and creates the sinkholes which we have, and some of the very erratic topography that we see in this area. Dolomite is similar to calcite in appearance, but it is more resistant to being dissolved, and has different types of it's just slightly different. It's not as likely to form this karst topography. And micas they form soft, extremely thin, transparent, translucent, elastic sheets. In fact, sometimes in the past, these sheets have been used for windows. And they tend to weather slowly to clay minerals. And they come in sheets, and they are very common in granitic rocks, gneiss, and schist. Rocks, we have a life cycle, which we talk about in our biology-based courses. We have a water cycle, which we're going to talk about later on in the semester, but this is the rock and soil cycle. And basically, most of the time, we start with magma or lava, and then we go to igneous rock. And then igneous rock decomposes under weathering to sediment, and then that sediment is usually a soil, and then that soil under lithification, which basically means it makes rock out of it, comes back into rock. And sometimes that sedimentary rock will decompose again. However, in some cases, the sedimentary rock is subjected to heat and pressure and becomes metamorphic rock. And then in some cases it'll melt and go back to magma cycles. There are parts of that cycle where you see more activity than others. But basically rock has a cycle. And the material is reformed and reused by chemical and mechanical action on it. Start with igneous rocks. Igneous rocks are solidified from hot molten rock material that originated deep within the earth. And it occurred either from the magma in the substance or the lava extruded during a volcanic eruption. We see this probably the volcano you see blowing up in the slide came from Mont Pelée, which is in the Caribbean. Hawaii, the big island of Hawaii, has several active volcanoes, and people who have the bad taste of living in the path of lava flows big trouble, get into big trouble from time to time. They owe their variations to the different chemical composition, regional magma, and the physical conditions in which the lava solidified. In other words, the magma in different parts of the world is going to have different, the basic material is going to be different. There are two major divisions. Extrusive is what we think of when we see a volcano blow. That's extrusive. It blows all over the place, and they're extrusive, or it flows down the mountain, and they're extrusive. They come out. However, as you see in this diagram, intrusive rocks basically usually never quite make it to the surface. But nevertheless, they are able to form, they are actually able to form areas of rock under the surface, even though they never make it to the surface. And this is an overview of the classification of igneous rocks, both intrusive and extrusive. Sedimentary rocks are stratified rocks. They're composed of chemical, biological precipitates, accumulations, or elastic particles. They are decomposed from existing igneous. In some cases, as I said, sedimentary rocks go back again. Basically, they are formed by a chemical solution that then, as I said, lithifies or returns to rock. Clastic sediments, are derived from the disintegration of existing rock masses. If it's volcanically ejected material that is deposited this way, they're called pyroclastics. Organic sediments have organic materials in them. If you have organic materials at the surface, have been growing, and they get trapped for whatever reason in a sedimentary formation, they come into the rock, and you can see those. This is a classification, the clastic and non-clastic. Most of what you see in this area are largely limestone, which are non-clastic. And so I spent an inordinate amount of time on those, because if you do the lab for this course, then you will encounter those. One thing that sedimentary rocks is that they lay down in layers. They lay down in layers, and they're this, and then they layer this layer and this layer. And changing conditions at the Earth's surface will vary those layers. Sometimes the sedimentation will stop and start again. But for whatever reason, either differences in the composition, the sedimentary rocks, by definition, are a layered type of thing, where they're not a homogeneous. They have this layer and this layer, and the boundaries between those layers are called bedding planes. And bedding planes are very important in the understanding of how to deal with sedimentary rocks. Metamorphic rocks are rocks that may be the igneous or sedimentary that have been altered physically. In other words, they start out as one of the other two, and with under heat and pressure are returned to a different state. They're divided into foliated and non-foliated, and of course, which are dependent on their formation and whatever whatever they were to start with. For example, non-foliated quartzite is in mostly fused quartz grains. Silicon dioxide, which we talked about earlier. If it's calcite or dolomite, it becomes marble. Metamorphic rocks, again, they're existing rocks, and usually it's intrusive. That because extrusive just kind of blows its stack and it's over with, but intrusive rocks are there. They're restrained, therefore they have more time to act upon what's around them. I'm not going to spend a lot of time on identification of rocks. I'll leave that for your lab and your geology courses. I obviously the identification of rock is important if you're in an area where a great deal of rock is actually exists and actually is part of your foundations. One thing that I want to emphasize here at the beginning is this: just because it's rock doesn't mean it's solid. And I've kind of danced around this, but I'll just make that important point. So we're going to put this thing on rock, and that's going to be the end of it. There's solid rock, and then there's not so solid rock, and we're going to show how we classify it in that way here in just a minute. Structural geology. There are different. The Earth's surface is constantly moving. It's a dynamic. It's not one of those things that just kind of sits there. If it did, then what we would have is a nice smooth surface with nothing. Pretty much it. But it's not. We have different. You've got, and most of this is, a lot of this is driven by tectonic considerations, particularly in high regions with large faults. We're going to talk about what faults are in a minute. But the Earth's surface is complicated because of its long formation, and because of its because of the different forces that have acted upon it over the many years. Let's talk about folds first. A rock body, there are different ways in which surface rocks, if you've driven, I know you have ridden along up to interstates in this area, and you'll notice that sometimes, sedimentary rocks, gravity would tend to indicate that sedimentary rocks should be horizontally deposited. Gravity being vertical, that they should be horizontally deposited. And yet you'll see routinely sedimentary, that's obviously sedimentary, they're layered. You can see the layers. Particularly if you're a newly cut roadway, you can see that very easily. And people say, well, why is it that they're not layered? Why is it that the layers are going like this? Well, the reason for that is very simple. The reason for that is that you have a situation where once were laid down and the sediments were deposited, they've been moved around. They've been moved around by tectonic forces in the earth, and or by other sediment, tectonic forces and other things going on have basically either slanted or bent sedimentation. And I emphasize sedimentary rocks because that's what we see in the area which we're at here at UTC. So I kind of focus on sedimentary rocks. A homocline, for example, as you can see, the sediments are pretty much flat. The sediments are pretty much the way they were laid down to start with. A monocline, for example, is due to a change of elevation. Part of the stratigraphy has basically either have moved which way, either this way or this way, relative to each other, and that too will bend the stratigraphy, so to speak. Anticlines are basically formations where the variation and the curvature is convex. And opposite to that, synclines are ones where they're concave. And these can be important in analyzing creek and river formations. And also you'll notice in those diagrams that in some cases the layers can be broken, and once you get that kind of break, then you can get once you get that kind of break, then erosion by a creek or a river or whatnot can further accentuate that. Faults, of course, in some ways are really the fault line of this whole thing, I guess. Basically, it's where a stratigraphy base has an abrupt change, and there are all different types of ways in which, and when fault, generally speaking, when fault lines move one against the other, you have an earthquake. And they generally don't, if you've got fairly old formations, fault lines will generally move slow enough where the earthquake's not too bad. But in newer geologies, they will sometimes move violently, and you will have very significant earthquakes. Okay, I've gone over a lot of the quantitative and qualitative stuff to get you to the quantitative material. One of the challenges which geologists and geotechnical engineers have faced over the years is normally speaking, we've been working from two-dimensional maps. But the Earth is anything but two-dimensional. I mean, if you're very flat, it's close to it, but it's still not really two-dimensional. It's all three-dimensional, and we're just trying to represent it. One way in which we can represent is, the bedding, how bedding planes and how rock formations actually vary in elevation is the thing called strike and dip. If you were to take a long ruler with a bubble in the middle of it, you were able to lay it down on the surface and get rid of the vegetation and whatever other surface interference you have and lay that down, and the bubble would be in the middle, then both ends of the ruler point to the direction which is called the strike. And the strike is basically the direction at which the elevation of the formation is uniform. The dip, and that's the strike. The dip is 90 degrees out, is the angle downhill basically from the strike. In other words, if you've got the strike is where it should be, then the 90 degrees should be the maximum downhill angle. And I won't go into the math behind why that's so, but in any event, that's referred to as the dip. The strike angle there's an important distinction we need to make between the strike and the dip angle. And that is that the strike angle is basically a cardinal direction. In other words, it's going to be either 0 or true north, or 10 degrees off north, or 20 degrees off north, 30, or whatever, go all the way around the compass rose back to 360. The dip is the slope of the formation going down from the strike. So they don't really measure the same. They don't measure it in the same plane. The strike is more or less in the plane of the Earth's surface, and the dip is actually perpendicular to that surface. This is a nice, the one on the left, traditionally this has been done with a Brunton compass. Now, of course, we've got electronic stuff. In fact, that's one of the big changes that we see in geotechnical engineering is the introduction of computer technology to do many of the same jobs we do, but with less effort, with a greater precision, if not necessarily accuracy, than we have done before. How accurate it is depends a lot on who's doing it, and how carefully it gets done. Geotechnical testing can be easily marred by poor execution of the test. The tests are not bulletproof, and they're bulletproof as they can get, but not perfectly bulletproof. And So measuring the strike and the dip, you see that you see how the strike and the dip are defined and how they're married with the Brunton compass. And of course, it's the Brunton compass you would have now is digital. And then you look on the right and you see how that's done on a map. You'll notice that the strike is in a cardinal direction, whereas the dip is again an angle from the perfectly horizontal plane. Now, in mentioning this, and I'm going to have some other material elsewhere on the topic, you have two things. The dip you see there is 90 degrees out from the strike, and that's the true dip. That's the maximum down. However, we also have something called the apparent dip, which is the angle which from the intersection from the strike line, other than the perpendicular from the strike line. In other words, maybe 45 degrees from the strike line or 60 degrees from the strike line, but not 90 degrees from the line, is an apparent dip. And I'm going to have some things on my site which will discuss the difference between the two and how you relate one and the other. Note also the orientation of the strike and dip relative to the cardinal directions as well. And these are your symbols you see in typical maps, how they're applied to geological maps. Geological maps and maps in general are an important way to start when you're trying to assess a site. And we're going to talk about site assessment a lot in this course and the next, because understanding site assessment is essential to understanding how we are to how we design and build on it. It's entirely possible, and I talk about this elsewhere, where a site which is in a good location from the standpoint of the structure in terms of using it is really poor from the standpoint of building it. And it's the wise community that heeds its geotechnical engineers' warnings in that difference. So how do we apply strike and dip? Well, we have to start with the assumption that if there's going to be sliding and failures in rock slopes, and we're talking about, obviously, if everything is flat and horizontal, doesn't vary, then life is good. However, as we all well know, in a mountainous region, that's not the case. And frequently we see cuts in the rock. There's good news. The thing about any, particularly with a stratigraphy that is layered stratigraphy, any layer stratigraphy, any sedimentary rock stratigraphy, the highest probability of failure is going to be at the bedding planes. All other things being equal. And that being the case, there's pluses and minuses. That the plus is, for example, if we need to rip the rock, if we need to take an excavator and put a special tool on it, and we want to rip that rock out, the best way to do it is to do it basically in the direction of the dip. In other words, where the tradition, typically with a it's directly basically in the direction of the dip, perpendicular to the strike, is the best way. The closer we can get to the true dip, the better. It makes it easier because we can wedge in between those bedding planes and break the rock up. On the other hand, if we want to cut a roadway, we are best to do it perpendicular to the strike, as you see in those diagrams. Sometimes we can do that, and sometimes we can't. And one of the reasons why we have rock falls is because in some cases that's just impossible. And then we have to live with the rock falls. Or we can do reinforcement of the rock falls or rock anchoring and that sort of thing. Weathering. Weathering is the physical or chemical breakdown of rock. Physical weathering is the unloading of overburdened compressive stresses, frost action, organism growth, temperature changes, crystal growth, or abrasion. And these are all physical weathering. It's not just outside in the rain, so to speak. There are all kinds of things that can happen. It can happen on the surface and sometimes happen under the surface. We also have chemical weathering. Oxidation, hydration, hydrolysis, carbonation, and solution, which we've discussed particularly with karst topography. These two processes are not mutually exclusive. They can be happening at the same time. Normally, how do we, we're engineers, our job is to quantify things. How do we do this? Well, how do we fix this? How do we design for this? Well, the first thing we have to do is take samples. And this is the first example of a sample from, in this case, rock samples. And these are real rock samples from this area, which were taken using a rock coring. Basically, the idea is that you core around the rock, usually using some type of diamond cutter, with the result that you get a nice cylindrical shaft of rock. Now, how solid that cylindrical shaft of rock is depends upon the integrity of the rock it's taken out of. If it's very solid rock, then it's going to be like the one on the left, which is fairly solid. If it's not, it's going to be more like the ones over on the right. And that distinction, however, is important because the most important single test that we do for rock in terms of the design of structures to go on rock is the RQD, the rock quality designation. It is based on a modified core recovery procedure. And basically, I think the best way is to illustrate how this works is to actually look at an example. So we'll look at this one, which is drawn from your Soils and Foundations handbook. The length measurements, first of all, there are certain rules that we follow. And let's look at over there on the left. On the left, we see the correct method, where first, always measure from the center line. If you've got a rock, and I'm going to go back a couple to make sure, you'll see that these are round. And basically what you do is you take a tape measure and you measure along the length of these samples. And you measure down the center line. You don't measure down one side or the other, but you measure down the center line. And basically, that's the first rule. Measure down the center line. Second rule is that the pieces that matter are the pieces which are 4 inches or longer. You measure the length of those pieces. And you measure the length of those, and those where you've got where you have sound pieces that are longer than 4 inches are the pieces which add to them. First of all, you start at the full length of the rock sample. Say in this case it's 48 inches by this example. What I want to do is to find the ratio between the sum of the length of the sound core pieces, which are greater than 4 sound core pieces greater than 4 inches, over the total core run length, which is 48 inches. And as you see in the box here, that's pretty much, they give the total length and they put it in the box that way, then they get another length and they put it in the box that way. All right, let's start with, look at the sample. At the very top, we have a 10-inch of solid core. At the very top. So we add that to it. The next length is L equals 0. It looks sound in this little diagram, but according to the geotech or the lab technician actually doing the adding up, it's highly weathered, doesn't meet standard requirements. Sometimes stuff that it doesn't have many fissures, have large fissures, may have a lot of little ones, and be highly weathered. The next one looks bad for everybody. It's the centerline pieces and little pieces, and you actually see this if you want to look at it. Look at the rock samples, the upper right-hand corner. You'll see some pretty mangy looking stuff up there, and that's probably not going to count because it's probably not 4 inches long and it's all broken up. And that's what I'm talking about. Then there's the next piece is 7.5 inches. The next piece is L0 for 4 inches. We do not count any rock, no matter how sound it is, any sample, any part of the sample which is less than 4 inches long. Then we have an 8-inch span. Now, this is probably the trickiest part of RQD testing. Rock is brittle for the most part, and it's very easy in the process of drilling and coring and recovering it to get mechanical breaks. Generally speaking, mechanical breaks are, particularly for fresh samples, are fairly easy to detect, particularly if you've done a lot. If you've got naturally occurring cracks and fissures, they tend to be of a different color, or they may have some wear relative to each other. But if you've got two pieces where you can see that it's obvious that it's a very fresh break, something that happened probably when it was being taken out of the ground, you count that even though there's a break in it because it's a mechanical break. You know, the rock can't help it that it was taken out. It was broken when it was taken out. And last but not least, L is equal to 0, no matter how long it is. If it's a void, it's a void. And you will see this often in rocks, particularly as you get closer to the surface. So therefore, what you do, basically, out of all those, we've taken basically 7 zones. Only 3 of them really count in the RQD. So we add the length of the top one, which is 10. The one, sort of toward the bottom, which is 7.5. And the last one with mechanical breaking was 8. We add those. You see the formula on the right. And we divide that by 48 and multiply by 100%. And we get 53%, which is fair. The rock quality description depends upon the zone. From 0 to 20, if we got 0 to 25, it would be very poor. 25 to 50 is poor. And 50 to 75 is fair. 75 to 90 is good. 90 to 100 is excellent. And that's how we evaluate rock quality. That's how we evaluate the RQD of a given rock sample. And we'll actually use these in evaluation of foundations put on rock. With that, we're going to try to transition to basic soil types. There are sedimentary soils, which are weathered in place. They can be residual or organic. Organic soils generally are not so hot. One of the things, they're good for agriculture. They're necessary. You have to really, for decent agriculture, you have to have organic soils, topsoil, and that kind of thing. For foundations, no. Organic soils are the result of the decomposition of living material. That which has been in process of decomposing will probably decompose some more. So it's not really what you want to have in a foundation. And then there's residual soils as well. And then transported soils, which are transported to deposit locations. There are all kinds of ways the earth moves stuff around. Alluvial soils, alluvial, glacial, marine, colluvial, and pyroclastic. We're going to talk about those. Sedimentary soils are residuals, are either got residuals or organics. I've talked about the organics already, peat or muck. Residual soils with sands, usually gravel, which is most of the time one of the big differences between rock and soil, maybe from a physical standpoint is the big difference that we need to consider, is the size of the particles. In fact, particles, this is a good time as any to introduce the key concept of particle size, because particle size is the single most important, not the only one, but it's the single most important quantity we deal with in soil mechanics. Sands tend to have, and obviously the largest would be gravels, and then smaller. Once you get past rocks, large rocks, they break down to gravels, and then they break down to sands, and then they break down, in some cases to clays, not always. They break down to sands, and clays are the very smallest particles. And many times, for example, a solution of carbonates and limestone, that's obviously going to produce a pretty small particle, which it does. And that's where you get a lot of your clay particles. Transported soils, with sedimentary soils or deposited, transported soils. One, alluvial soils. River deltas are the most best known way of doing that. And deltas can be very large or very small, depending upon the river that's actually doing the depositing. River delta formations can also take place further inland, and probably some of the most complicated formations in the Mississippi River Valley, which particularly once you get below Cairo, Illinois, you get down to Arkansas, and to a lesser extent West Tennessee, Mississippi, and Louisiana. There's a lot of delta types alluvial deposits all the way up. And there are all kinds of soils are constantly being eroded from higher elevations and deposited in lower ones. And those deposits and the history of that can lead to some very complex, geographically complex, such as your meandering rivers, which change course. Oxbow lakes, which are rivers which are left behind a certain bow, and then finally at the end, the delta itself. It's interesting to note that particularly the Mississippi River Delta itself has been one of the most abused, I don't know the way to put it, geological formations in the country. The reason for that is this. Until about, I'd say about the 1960s, the flow down from the upper elevations of the Mississippi actually grew the state of Louisiana through New Orleans, because they had a constant flow, they had a constant supply of basically small particles to build up the delta. Because the core, for flood control purposes, and because the Corps was trying to avoid the Mississippi River changing course from the Mississippi River to the Atchafalaya River over between Lafayette and Baton Rouge, the Corps developed a system of channels and whatnot that basically channelize the flow of all of the sediment, the alluvial settlement. So therefore, not only did the delta stop growing, it actually retreated. And actually, Louisiana has been shrinking for a long time. The thing that finally got that, the piper finally got paid in Katrina. Between the lowering between the lessening of all of those alluvial areas, the Mississippi River Delta itself, the areas to the west of it in Lafourche and Terrebonne Parish, the areas to the east of that in St. Bernard Parish, were all in retreat. They were all sinking. And when Katrina came along and did not provide the protection for New Orleans and that area and a lot of major cities that you need to that the alluvial deposits that were there before provided it. And as a result, that was one of the major causes for the disaster that was Katrina. So now the Corps is attempting to undo a lot of that and to try to get it so that the alluvial coming down from here and other places in the United States is rebuilding the Mississippi River Delta area. One of the things about environmental engineering is that it's important for civil engineers and environmental engineers to look at all of the potential consequences of what they do, because sometimes it may not work out the way you think it does. Alluvial fans, these are in mountainous areas where you get deposits from mountains, and water is basically deposited them in lower areas, such as Piedmont deposits. Aeolian soils are soils that are transported by air, and the most famous of those are your low S's. We'll talk about those when we get to expansive and collapsible soils. Low S's is an amazing material in that you can actually cut vertical cuts in it. That's the good news. The bad news is that with water change contents, it will collapse on you. So, and also produces some fairly rugged looking, because of that ability to do vertical cuts, it can produce some very rugged looking stratigraphies, even in areas where you don't have a lot of elevation. You wouldn't expect a lot of elevation change. Glacial soils. The last ice age, and there's been more than one, have come down, and the glacier sheets were very large and thick and exerted a pressure on the soil below them, and they did a lot of damage. In the meanwhile, they would dig stuff, dig into the earth, and then when they left, they would deposit stuff back in the earth. But they created probably one of the best known glacial soils to be your glacial tills. And your glacial tills are the result of pressure being applied by the glaciers, but when the pressure went away, the compaction of the soil and the consolidation of the soil meant that the soil was more compact and actually makes an excellent foundation material if it's on the surface. It's not always on the surface, though. Glacial tills are many times below the surface, and we have to basically drive deep foundations to get the benefit of the glaciers. That brings, of course, that of course is the main cause, but not the only one, of pre-consolidation and over-consolidation. We'll talk about that when we get there. There are other marine soils. One thing you must understand about marine soils, and this is kind of a pet peeve of mine, is that in the last particularly 50 years, people have built developments in coastal areas that really didn't need to be there. Coastal areas are nice. You got the waterway, or you got the ocean and whatnot, and everybody loves to live there. The problem is that coastal areas, and some are more than others, are by their nature not very stable. They are the place where the land and the sea meets. The sea will deposit soils, the sea will take away soils, the sea will do this. And a lot of attempts to stabilize them have had mixed degrees of success. But in any case, much of the building along the coastal areas is to use, from one government publication, talking an active hubris or pride. And that pride has been knocked down with many hurricanes. And that's why everybody likes to live on the beach until the beach decides it doesn't like you anymore. And then you're in trouble. There are also colluvial soils, material transported by gravity, which are basically downhill flows of soil, particularly in hills. And these are not always, unlike alluvial soils, they're not driven by water, they're driven by just gravity, where they decompose, they come down. They're generally not the greatest of foundation materials because they're on the move now. They've been on the move recently, and they're not well consolidated or compacted. One other concept I want to talk about is soil cohesion. Cohesional soils are generally grain or coarse grain. They talk about that grain size thing I talked about earlier. They don't necessarily adhere to each other and have higher permeability. On the other hand, a cohesive soil are fine grain. They have a natural attraction to each other due to the presence of clay minerals, and they have a low permeability. And this distinction between cohesionless soils and cohesive soils is very important. It's one that you will see. It is one of the most important. I say that grain size was the most important. Well, I got to make sure I'm pointing in the right direction. This is kind of weird. This distinction right here is also important, and it's related to the grain size. Generally speaking, cohesive soils are fine grain, cohesion soils are coarse grain. So you must understand that that the two are related to each other. This distinction is one that I will go through repeatedly in this course and the next one. One of the other when you get into very small particles, we get structure of clay minerals. Cohesionless soils they don't adhere to each other chemically. They don't have a chemical bond. You'll get apparent cohesion every now and then, but usually that's not very important. Atoms of clay minerals form, and in cohesive soils, you do have clay bond. The particles actually have a chemical bonding to each other, either in silica, tetrahedral sheets, alumina, and they can layer in different ways, forming different. And clay minerals tend to form flat plate-like shapes in the soil, and they adhere to each other depending upon water content and chemical composition and that sort of thing. The most prevalent is kaolinite, one sheet alumina, one sheet silica, back and forth, back and forth. Most common. Halloysite, if you take water out of halloysite, you get kaolinite. Illite is more plastic than kaolinite, and you see mostly in marine deposits. The real stinker is montmorillonite, named after Montmorillon in France, where this soil was first identified. It has the same as illite. The silica and aluminum, and one silica, one aluminum, one silica sheet, and they're bonded with potassium, except there's no potassium in montmorillonite. Iron and magnesium in place of the aluminum. These are your expansive clays. We're going to talk about this in foundations. These clays can be real stinkers to design and build on. They can be real stinkers. If you have changing water content, they will expand. And when they expand, they can be very destructive. And this is a summary from the Navy's document DM7 of soil deposits. And you can read that, even though I've covered most of it in the rest of this presentation. And that concludes our first lecture. Thanks for watching, and God bless.